This is B. Naresh, working as an assistant professor in ICARE department. Today we'll see the problems on load line analysis of BJT. And before going to this today's session, what is the importance of the load line analysis? So in this case, we have the two types of the load line analysis. One is the DC load line analysis, and the other one is the AC load line analysis. And these two load line analyses are used to determine the operating point, that is nothing but a Q point. So based on this optimum operating point, we are defining as the particular transistor is acts as a perfect amplifier, means it produces the faithful amplification without any distortion. So to define or to design a amplifier by using this bipolar junction transistor, we need to define the proper operating point. So hence, to determine this proper operating point, we need to perform the load line analysis concept for the bipolar junction transistor by using the DC load line analysis as well as the AC load line analysis. So in this session, we are going to see some of the problems, how to identify the DC load line analysis and the AC load line analysis, as well as the Q point. So let us consider the first problem. Determine the maximum voltage swing at the output of common emitter amplifier in which the quotient point is ICQ is 0.9 milliamperes and VCEQ is 9 volts. The AC resistance seen at the output terminal, that is RAC. So generally the AC resistance is a parallel combination of the collector resistance as well as the load resistance. So in this problem, they are directly providing the AC resistance, that is 2 kilo ohms. So hence, so from this problem, we need to find out what is the maximum voltage swing at the output of the common emitter amplifier. Means they are using the CE amplifier. So in a CE amplifier, we know that input is passing through the base and output is measured across the collector terminal. And in the problem, they are defining the quotient point. So the quotient point is also called as the operating point here. And it is also called as the Q point. So generally, if we need to define this Q point, actually the Q point is located in an active region, and that is actually the center of the DC load line. And how we can say that the transistor is in an active region? For this case, the emitter base junction is forward bias and the collector base junction is a reverse bias. We can say that that particular transistor in an active region. So in that active region, the transistor is acts as an amplifier, but we need to find out in that entire active region, the transistor is not acts as a faithful amplification, but we need to find out what is the exact operating point or the quotient point, or at which point the transistor is exactly acts as a amplifier without distorting any input signal. So for this case, they are providing the operating point. So this operating point, the Q point, is a functioning of collector current as well as output side. So we need to take only the output side. So if you are consider the common emitter amplifier, let us consider emitter is a connector. And here we make an as this is connected to VCC. Here we are going to measure the output V0. And this is the collector resistance, and the input is passing through this base terminal. At this point, now we need to measure how much collector current is flows, as well as the potential difference between these two terminals, collector and emitter, that is represented as VC. Hence, at the output side, these two parameters reflects. So hence, collector current and a VCE. Hence, this VCE voltage as well as the collector current is also defines the optimum operating point. Hence, it is represented as The operating point is a functioning of IC and VCE. Hence, in a problem statement, they are represented that ICQ value is 0.9 milliamperes and VCEQ is 9 volts. And also they given that the RAC, that is the name of the parallel combination of collector resistance and the load resistance, that is approximately equal to 2 kilo ohms. Now by using this one, we need to find out the maximum voltage swing. Hence, here I'm going to choose. So first, I'm going to find out how much a peak-to-peak AC collector current is flowing through that given amplified circuit, common emitter amplified circuit. That can be defined as, it is defined as delta IC, that is equal to 2 times of ICQ. So why we taken as, generally the Q point is defined as, it is the center of the DC load line. So hence the DC load line contains VCE parameter and IC parameter. If you want to define the Q point, that is the center, means half of the VCC and half of the collector current. So from this, so here we need to find out how much maximum a peak-to-peak collector current is required. Hence, it is 2 times of your Q operating point, and this operating point is related to, means in this case, the Q point is a functioning of, so that is a center of the DC load line. The DC load line contains VCE parameter as well as the IC parameter. Hence, we take in the center of the point that indicates the Q point. So from this, we need to find out. So means this Q is a functioning of IC and VCE parameter. Hence, so these are the two parameters indicates the optimum operating point. From this, we need to calculate how much maximum peak-to-peak collector current and what is the maximum peak-to-peak voltage is generates across the collector and emitter terminal with respect to the emitter terminal. So from that representation, we require as, this is the maximum peak-to-peak collector current is defined as 2 times of ICQ. So hence this is 2 into, so if you observe the ICQ, so in that ICQ they given that 0.9 milliamperes, hence this is 0.9 milliamperes. So hence it is 2 into 0.9 into 10 to the power of minus 3 amperes, hence that is equal to 1.8 milliamperes. So this is delta IC. So that is the reason delta IC is represented as 1.8 milliamperes. Similarly, we need to calculate what is the maximum peak-to-peak voltage is flows in a common emitter amplifier circuit. Hence, I'm going to represent the maximum symmetrical peak-to-peak output voltage. It is represented as delta VEC, that is equal to delta IC. V is equal, means generally we are representing like this. V is equal to the product of current and resistance. And this output voltage is related to output collector current along with the output resistance, that is AC resistance. And AC resistance, generally they given that this AC resistance is parallel with the collector resistance and load resistance. In our problem statement, the AC resistance, they are providing this AC resistance is 2 kilo ohms. And IC, delta IC, just now we got the delta IC is equal to 1.8 milliamperes. Hence, so by using these two statements, now we are going to calculate what is the maximum peak-to-peak output voltage for a given common emitter amplifier circuit. Hence, it is represented as 1.8 into 10 to the power of minus 3 into 2 into kilo ohms, means 2 into 10 power 3. So this minus 3 and 10 power 3 is a get cancel. 1.8 into 2, that is equal to 3.6 volts. So the units are volts, but because of that we are going to measure the voltage. That is the reason the delta VEC is represented as 3.6 volts. So from this, we identified the maximum symmetrical outputs in terms of voltage and the current. The voltage is 3.6 volts and the current is 1.8 milliamperes. These are the 2 points we observed from the given statement. Now see another problem. In the transistor amplifier shown in below figure, let RC is a 8 kilo ohms, means this is RC. So collector resistance, RC indication is collector resistance. RC is the 8 kilo ohms and the load resistance is 24 kilo ohms, means this is RL. RL is the 24 kilo ohms and VCC, it is a bias with a 24 volts. And for these specifications, we need to draw the DC load line, as well as we need to determine the optimum operating point. So optimum operating point means we need to determine the Q point, and also we need to draw the AC load line. So hence we need to find out from these specifications, we need to find out the DC load line and the Q point parameters, as well as AC load line parameters we need to parameter. So DC load line parameters we need to calculate, Q point parameters we need to calculate, as well as AC load line parameters we need to calculate. From all these specifications, so finally we need to draw the a load line diagram. So from that, in that we need to represent DC load line, AC load line, as well as the Q point. So for this case, based on the given figure representation, given within the circuit, and here we used as common emitter amplifier circuit, CE amplifier circuit. So why? Because of that, emitter is a common for input side as well as the output side. Hence, the given circuit is acts as a common emitter amplifier circuit. It is a biased with a VCC, so that is 24 volts. But again, you should remember, and we need to define here the transistor is acts as a amplifier, means we need to make sure that the input junction should be forward bias and the output junction should be reverse bias. And that is the reason, and we consider this is the NPN transistor, and output side we need to make the reverse bias. Hence, N is a bias. This collector terminal is biased with the positive pole of the battery, and that is represented as a plus VCC to make the output junction is reverse bias. So based on the given specifications, what are the given specifications? They given that the collector resistance is the 8 kilo ohms and the load resistance is the 24 kilo ohms and the VCC is the 24 volts. So by using these three specifications, first I'm going to calculate what is the DC load line, and then from that we need to define the optimum operating point at a Q point. Then we need to find out the AC load line analysis concept. To identify this a DC load line conditions, so the DC load line is also contains the parameters like IC and VCE parameters. Hence, and let us consider to identify this DC load line condition, we need to make in the absence of AC signal. In the absence of AC signal, now we need to find out the equivalent DC load line circuit. And for this given circuit, in the absence of AC signal means, so under the DC signal condition, the capacitor is acts as a open circuit. Capacitor is acts as a open circuit. Hence, the V is removed from this network, and here also the load resistance is removed from the output node. Hence, that equivalent circuit. So under the DC load line analysis, the equivalent circuit shows like this. So it is a bias with RB, and it is connected with a base and a collector. Emitter is connected to ground, and the collector is biased with RC with a DC biasing source is plus VCC, and emitter is connected to ground, and this is your output node V0, and that V0 is nothing but a VCE parameter here. And this is the DC equivalent circuit. So why? Because of the we are going to find out this DC load line and the absence of given AC signal. So under the DC conditions, this coupling capacitors and the bypassing capacitor CC and C. So here this is a coupling capacitor CC and the CC. So these two capacitors, see, these two capacitors are acts as a open circuit. Hence, the input signal is not connected to base. AC signal is not connected to base. And similarly, the load resistance is also not connected to collector node. So hence the equivalent circuit shows like this. So from this circuit, now we need to determine the DC load line parameters, that is IC parameter as well as the VCE parameter here. So to identify this IC and VCE parameter, now we need to apply the KVL at this output side. So what is the KVL equation? So if you want to write the KVL equation, that VCC is equal to the voltage drop across this collector resistance is represented as IC times of RC plus, and here the voltage drop between, or the potential difference between collector terminal and emitter terminal is represented as VCE. So hence, so from that given figure, and when I consider the circuit in the output loop, so I represented this one. So hence the same what we discussed just now. So hence from that given circuit, VCC is represented as the voltage drop across the collector resistance is represented as IC times of RC plus, and the potential difference between the collector and the emitter, that is represented as VCE. So here from this circuit, if you want to find out a output voltage, so we need to, which one is the output voltage? VCE is acts as the output voltage. Hence, the VCE is equal to, take this out, this term outside. So hence VCE is equal to VCC minus IC times of RC. So by using this equation, we need to find out the maximum collector current and the maximum output voltage under this DC condition. Hence, if let us take in this relation, if your collector current is 0, so what happens if collector current is 0 means VCE is equal to VCC minus 0 times of RC. That is the reason. So VCE is approximately equal to VCC point. So if you want to draw this characteristics, means the x-axis is represented as VCE and the y-axis is represented as IC. When the current is 0, VCE is equal to VCC parameter. So let us say this is VCE is equal to VCC parameter. Similarly, when if a VCE is 0 in this equation, if a VCE is 0, what happens here? That is 0 is equal to VCC minus IC times of RC. From this, I am going to find out this IC. So when you are substituting here, so means VC is equal to 0 is equal to VCC minus IC times of RC. From this, I am going to find out the IC parameter. So what is IC here? This IC is equal to VCC by RC. And if it is a maximum, so IC maximum, that is so hence, if a VC is 0 volts, the collector current is represented as VCC by RC. The intersecting of these 2 points, is nothing but a DC load line. So in this DC load line, if you want to define the optimum operating point, so based on the theoretical concept, the Q point is always the center of the DC load line. So means we need to take the center point. So this is half of the VCC and this is half of the IC value, that indicates the Q point parameter. So hence, then now we are going to calculate based on the given problem statement. Now we need to calculate how much VC voltage and how much collector current is generates based on the given specifications. So let us consider again from the given statement and from the figure. Now we need to calculate, to define this DC load line, we need to calculate the VC parameter, that VCE is equal to what we observed. So in the statement, we observe that VCE is equal to VCC parameter. Hence, and from that relation, so VC is equal to VCC. So in a given problem statement, they given that VCC is the 24 volts. Hence, VCC is equal to VCE is equal to 24. Now we need to calculate IC. What is IC? IC is equal to VCC times by RC. So VCC is 24 and RC value is, so in the problem RC value is 8 kilo ohms, and you can substitute RC value is 8 kilo ohms. So this is 8 kilo ohms, means 8 into 10 power 3. So means what happens, 8 1 there and this is 8 3 there. That is the reason IC is equal to 3 by 10 power 3 is nothing but a 3 milliamperes. That is the reason the collector current is represented as IC is equal to 3 million. So in this, to define this DC load line, so what are the parameters we observed? VCE is equal to 24 volts and IC is equal to 3 milliamperes. So by using these 2 points, now we can draw a load line concept, that is nothing but a DC load line. I will show at the end of this problem how to draw the DC load line and a Q point. Now the next thing is, in a problem they ask that to determine the Q point. So hence we need to find out the optimum operating point Q. So what is the optimum operating point? We know that the Q point is always located in the center of the DC load line to define a perfect amplifier. So hence we need to mark the middle of the DC load line and corresponding to VCE and IC values. So to define this Q point, so what is the VCE? VCE is equal to VCC, that we observed that 24 volts. If you want to define the Q point, what is the Q point? That should be, we need to differentiate VCEQ. So the same parameter we are defining in terms of the Q point, that is represented as VCEQ. That VCEQ is half of the VCC, means 24 by 2, that is nothing but 12 volts. Hence, from that we know that VCEQ is 12 volts. So hence I represent the same. And similarly, we need to calculate IC. What is the IC parameter? ICQ. So based on the statement, ICQ is also the center of the DC load line, hence I need to write half of the IC. So IC value is 3 milliamperes, means 3 into 10 power minus 3 amperes by 2. That is nothing but a 1.5 milliamperes. So ICQ is 1.5 milliamperes. Hence, so what are the parameters we observe? VCEQ is 12 volts, but VCE is 24 volts. IC is 3 milliamperes and ICQ is 1.5 milliamperes. Now we need to calculate. So then we need to also, means if you observe the amplifier circuit, the amplifier circuit is the superimposing of the AC signal and DC signal. So hence we need to find out the AC load line analysis concept also. So to determine this AC load line analysis, so means based on the theoretical concept that AC load line is also passing through the Q point as well as DC load line concept. So based on that, so we are going to define, if we want to draw an AC load line, we need to calculate the maximum VCE parameter as well as the maximum collector current when your input signal is upright. Means in the presence of given AC signal, we need to find out how much maximum output voltage and how much maximum collector current is produces with respect to the DC biasing and with respect to the given AC signal. So before going to this signal, so if you observe the circuit, let us for the given amplifier analysis concept. So when the presence of AC signal means when we consider the input signal is passing through the input of the amplifier circuit, here these capacitors, the coupling capacitors, it acts as a short circuit. Why? Because of that capacitor is allows the AC signal. Hence, this capacitor, input side capacitor and output side capacitors, or acts as a short circuit. We free the short circuit at the output side, and from this representation, this collector resistance is The parallel combination with a load resistance, that is the equivalent resistance, we represented as RAC. The equivalent AC resistance based on the presence of given input signal, it is represented as, it is a parallel combination of collector resistance and load resistance. Hence, now first I'm going to, before to identify the AC load line concept, first I'm going to calculate the equivalent AC resistance. So from this way, I can represent this. So we have this collector resistance is 8 kilo ohms and load resistance is 20 kilo ohms. Now what is RAC? RAC is nothing but a parallel combination with RC and RL. Hence, it is represented as RC into RL by RC plus RL. So where RC is 8 kilo ohms means 8 into 10 power 3 into RL is 24 kilo ohms, 24 into 10 power 3 by the summation of RC resistance means 8 into 10 power 3 plus 24 into 10 power 3. You can solve this one. It gives that RAC value is 6 kilo ohms. Now we need to calculate the maximum VCE point and the maximum IC point to determine the AC load line. Hence, I'm going to find out the maximum VCE. The maximum VCE is represented as VCEQ plus ICQ into RAC. So we observe that VCEQ is 12 volts, hence this is 12 plus ICQ, we observe that 1.5. ICQ is 1.5 milliamperes. Just now we saw this one. So 1.5 into 10 to the power of minus 3 and RAC is a 6 kilo ohms. So we know that this RAC is 6 kilo ohms and 6 into 10 to the power of 3. So 10 power 3, this 10 power minus 3, they get cancelled. Then let's solve this one. It gives that. So then that gives that. So means this is 12 plus 9. That is the reason the maximum VCE is 21 volts. So that is equal to VCE, maximum VCE parameter. So similarly, we need to calculate the maximum collector current, that is represented as. So means that if you observe this one, so means when you are drawing the AC signal, that is AC signal is a superimposing of the DC signal. So hence, that AC signal is also passing through the optimum operating point. That is the reason. While calculating the VCE, we take as optimum operating point along with the AC voltage, means V is equal to I into R. Similarly, for calculating the maximum collector current, this the collector means it's also passing through the a operating point. That operating point is represented ICQ. Then in terms of current, V by R, VCQ by R is. So hence we know that ICQ is 1.5 milliamperes. Hence, so it is represented as 1.5 into 10 to the power of minus 3 plus VCEQ. VCEQ we observe the 12 volts by RAC is a 6 kilo ohms, means 6 into 10 power 3. So by solving this ratio, it gives that the maximum IC value is 3.5 into 10 to the power of minus 3 amps. Now by using all these parameters, we need to draw the load line graph here. So hence, here I'm going to utilize, means the x-axis is represented as a VCE. So y-axis is represented as the collector current. So first we need to draw the DC load line. So if you want to draw the DC load line, what are the DC load line parameters? We observe that VCE is equal to VCC, that is equal to 24 volts, and IC is equal to, we observe that VCC by RC, that is 3 milliamperes. So hence, first I represented this is at 24 volts and IC is 3 milliamperes. By intersecting of these two, means 3 milliamperes and 24 volts, means the curve I represented this A and a B. This intersecting of A node and a B node is acts as a DC load line here. And similarly, after that, we need to find out the Q point. What is the Q point we observed? VCEQ, second case. and we observed ICQ. VCQ means that is the center of the DC load, that means 12 volts, and ICQ means center of the collector current is 1.5 milliamperes hence. So we place this is the 12 volts and we place this 1.5 milliamperes. So that intersecting of this point on a DC load line is nothing but a Q point. Now, and based on this, now we need to find out the AC load line. So in a AC load line, we observe that maximum VCE as well as we also observe that maximum IC. So what is the maximum VC? We observe 21 volts. Maximum IC value we observe that 3.5 milliamps. Means again, so this is the 21 volts and the maximum IC value is the 3 point. Means then this is the C node. I create the C node and here I create the D node. The intersecting of the C and the D is passing through the Q point. That line, the intersecting of the load line is called as the AC load line. So these are the specifications based on the given specifications we observe the Q point values as well as the DC load line and the AC load line parameters. So similar to this one, now we are going to observe another problem. For the transistor amplifier shown in below figure, VCC is 12 volts. Let R1 is a 8 kilo ohms, R2 is a 4 kilo ohms, RC is a 1 kilo ohm, RE is a 1 kilo ohm, RL is a 1.5 kilo ohms. Assume the VBE, means this is the VBE, the potential difference between base and emitter is a 0.7 volts. Now we need to draw the DC load line and again we need to determine the operating point and we also draw the AC load line. So based on this, all these specifications and based on this potential divided network, we given that a potential divided network, but in the previous problem we observed that by using the fixed bias network method. So in by using the fixed bias network, we observed again there is no emitter resistance in the previous circuit. But in this case, we also have this emitter resistance. So means the collector current is also passing through RC as well as the emitter resistance. Means while determining the collector current, we need to consider the collector resistance as well as the emitter resistance. So we'll see how it will be different compared with the previous problem statement. Now, so first we need to find out the DC load line. And we know that in the absence of given AC signal, we need to find out the DC load line analysis at the output side. Means we need to consider this point. So this C is removed. So why? Because of that, this capacitor is acted under the DC condition. This capacitor is acted as a open circuit. Hence, we need to take from the VCC node to this lower potential. So this one VCC is equal to the voltage drop across the collector resistance as well as the voltage drop across the emitter resistance. So if you consider that one, VCC is equal to IC times of RC plus again IA times of RE along with the potential difference between the collector and emitter is represented as VCE. And generally for the transistor configuration, we know that the I is equal to the summation of base current and collector current. And based on the construction principle, if the base width is very small, hence if the base current is very small, IE is approximately equal to IC. Hence, and for this case, I am writing this one IC times of RC. IE is replaced with again IC times of RE plus VC. So from this, we need to determine the VCE parameter. Hence, so here I taken as from the circuit. The VCC is represented as IC is flowing through RC along with RE along with the VC. So from this we need to find out the VCE. VCE is equal to VCC minus IC times of RC plus RE. Now we need to find out how much VCE voltage and how much collector current is generates here. So for this case, one time we need to substitute the collector current is a 0. If IC is a 0, again the VC is equal to VCC, means this is 0 times of something 0. Now if you want to determine the VCE, means collector current, now we need to substitute VCE equal to 0. If a VCE is equal to 0, VCC that is 0 equal to, So 0 equal to VCC minus IC times of RC plus RE. From this relation, now we need to find out this IC. What is IC? VCC by RC plus RE. So by using these two mathematical representations, now we need to calculate the VCE parameter and IC parameter. Hence, now from the given specifications, they given that VCC is a 12 volts. Hence, from the previous statement, so we know that the VC is equal to 12 volts. And similarly, we need to calculate the IC parameter. What is the IC parameter? VCC by RC plus RE. So we given that VCC is 12 volts, and we need to find out what is RC and RE. So in that, the RC value is they mentioned that 1 kilo ohms, and RE is also they mentioned that 1 kilo ohm. Hence, we need to substitute RC values and RE values here. So hence VCC 12, RC is a 1 kilo ohm plus RE is also 1 kilo, means 12 by 2 into 2 kilo ohms. So then it becomes 6 milliamperes. Hence IC is equal to 6 milliamperes. Now by using this one, we need to calculate the Q point. But before going to calculate this Q point, so first we need to find out. So basically, this is the voltage. They given that voltage divided network. Hence, we need to find out how much voltage drop is generates across this R2 network. So how to find out this one means, so we can use the voltage division ritual. So I into R2. So I means again V by total resistance. Hence, I use the same representation voltage division rule to determine the how much voltage is flowing across the R2, that is represented as. So at the output side, so this is the network we have. This is R1 and this is R2. It is connected here. This is base side. It is a bias with plus VCC. Now I am going to find out how much voltage drop across this R2 resistance. Means that is nothing but a I into R2. So from that, I is equal to V by R. V means VCC by R means total resistance. Total resistance is R1 plus R. So that is the reason. And this is I into R2 means into R2. So that is the reason. R2 by R1 plus R2 times of VCC. Now you can substitute this R2 and R1, R2 values here. The R2 value is 4 and R1 is 8. So R2 value is 4 kilo ohms and R1 value is 8 kilo ohms. So R1 is 8, R2 is 4 kilo ohms. Hence, so this is into VCC is 12 volts. Now you can solve this one. This is 4 into 10 power 3 by 8 plus 4, 12 kilo ohms into 12 volts. So hence that VC is equal to, means this 12 is a get cancel. So 10 power 3 is a get cancel. Hence the V2 is 4 volts. Now from this, now we need to calculate. If you observe the circuit, so what is the circuit? It contains this we observe. So means from the given circuit, this is the input side. Just I am drawing the input side. This is biased with a plus VCC, and this is a node. It is connected to ground. R2. It is connected to base. So it contains a RE resistance, emitter resistance. Now this can be replaced with this node voltage. Now we represented as a V2, and it contains it connected to base of the transistor along with this RE. So hence, so from this, what is this here? This is potential difference between base and emitter, and here the current is flow size IE. So if you want to apply the KVL at this input side, now we can write this V2 is equal to VBE plus IE times of RE. That is the reason I represented as V2 is equal to VBE plus IE times of RE. Now we know that VBE is equal to 0.7. And from the transistor construction, we know that IE is equal to IC. Hence, you can substitute this one. Then, so or otherwise you can calculate from this IE. So hence, IE is equal to, from this relation, V2 minus VBE by RE. V2 is how much? V2 voltage 4 volts minus 0.7 VBE. RE they given that 1 kilo ohm. So means 4 minus 0.7 means 3.3. So by 1 into 10 power 3 means that is equal to 3.3 milliamperes. That is your IE value. So hence IE is equal to 3.3 milliamperes. Now from this circuit, now we know that the collector current is approximately equal to emitter current. Hence, what is the IE value? IE value we got that 3.3 milliamperes. Hence, IC is also becomes 3.3 milliamperes. So hence IC is also 3.3 milliamperes. Now again from the output side we calculated this VC is equal to VCC minus IC times of RC plus RE. So from this case now we can substitute this VCC value 12 minus IC value is 3.3 into 10 to the power of minus 3 and RC is 1 kilo ohm plus RE is also 1 kilo ohm. So means 1 plus 1 2 kilo ohms and 2 means this is 12 minus 3.2 means 6.6. So that is 6.6 into 10 power minus 3 into 10 power 3. So 12 minus 6.6. That is nothing but a 5.4 volts. So this is VCA value. So now, so that is means VCE value. This is nothing but a VC value is nothing but VCQ. IC nothing but a ICQ. Now we need to calculate the AC load line. So for this AC load line, so that AC load line means in the presence of AC signal, we need to first determine the equivalent output side. So the output side we have the two resistances. One is the load resistance as well as the collector resistance. Hence, first we need to find out the equivalent AC resistance. That can be divided by RAC is equal to RC the parallel with the RL. So where they given that RC is a 1 kilo ohm and RL is a 1.5 kilo ohms, hence RAC is equal to 1 kilo ohm into 1.5 into 10 power 3 by 1k plus 1.5k. Then you can simplify this one. It gives that RAC is equal to 0.6 kilo ohms. Now by using this one, now we need to find out what is the maximum VCE parameter and what is the maximum collector current here. Hence, to determine this maximum VCE, we know that VCEQ plus ICQ times of RAC. So what is the VCQ we observed? VCQ is 5.5 volts. So hence, so this is 5.5 volts means ICQ we got that 3.3. So 3.3 into 10 to the power of minus 3 into RAC 0.6 kilos. Kilos means 3. So this 10 power minus 3, 10 power minus 3. Then you can simplify this one. Now this maximum VC that is equal to 7.38 volts. Similar to that, we need to find out the maximum collector current. So hence the maximum collector current is represented as ICQ plus VCQ by RAC. So ICQ value is 3.3 milliamperes plus VCQ is 5.4 divided by RAC value is 0.6 kilo ohms and this is 0.6. Then let's solve this one. It gives that the maximum IC is 12.3 milliamps. Now by using all these statements, we observe the DC load line and optimum operating point, and we also observe the AC load line parameters. So by using all these three parameters, we need to draw the response of this load line analysis. Hence, the x-axis we taken as a VCE and the y-axis we need taken as a value. First, we need to draw the load line. The load line contains VCE is equal to VC, and IC is equal to VCC by RC. We got the some values. When VC is equal to VCC, that is the 12 volts, and that is VCC by RC. We got that 6 means the intersection of this A and B, it indicates that DC load line. Then we also observe the Q point parameters based on this voltage division with 4. We observe that VCQ is equal to 5.5 volts and we got this ICQ is 3.3 milliamps. Hence, I need to define. So this is this point. So it indicates this is 5.4 volts. And whenever it intersects this y-axis, that is we taken as 3.3 milliamperes. That intersection of these 2 points. So hence I given that this is a 5.4 volts and 3.3 milliamps, and these 2 wires intersecting on a DC load line that defines the Q point. Then after that, we identified the maximum VCE and the maximum IC. So what is the maximum VCE value? We got that maximum VCE value is 7.38, and the maximum IC value we got that 12.3 milliamperes. So hence, so this IC maximum IC value is 12.3 milliamperes, and a maximum VC value is 7.38 volts. The intersection of these 2 points, C and D, is nothing. That is passing through the Q point, and this line is called as AC load line. So from the given specifications, we observe this DC load line parameters as well as the Q point and AC load line. So up to this point in this today's session, we observed that the load line analysis of problems on load line analysis of BJT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.